So let's now continue in English. Lectures on antenna and propagation. In the first lecture, so today, all the 3 hours today, we actually have just to repeat old things that many of you have already heard. Some partially, some completely, some people completely, and some people have not heard anything about this. So if I talk about things we need here, we need some mathematics, and many of you do not have mathematics 3. Have only mathematics 1 and 2. Differential geometry in free space is mathematics 3. Partial differential equations is mathematics 4. So many of you didn't have this thing. Further, many of you didn't take the course of electrodynamics. We shall also repeat things said with the course of electrodynamics. Electrodynamics is a continuation of the fundamentals with more mathematics. With mathematics 3 and 4 you heard in the second year if you are the university course. So the first thing, now all 3 hours I will be just repeating. First hour just geometry, second hour electrodynamics, and third hour antennas. Antennas that already we had this introduction in the electrodynamics course, but this is all repetition from the old from courses you already had. Many of you already had these courses at the university. In physics we have different quantities. We have scalar quantities, like mass, that is given in kilograms, and this is a scalar. A mass does not have any direction. And we have vector quantities in physics. Vector quantity is like a force that is given in units of Newton. It has both a magnitude and a direction. So what kind of calculations we do with these quantities? Well, students usually prefer to, if they find a problem, they multiply two quantities or they divide two quantities, and they shrink all the problems to multiplication and division. And they simplify everything. If a certain problem requires the computation of a square root, that's already difficult for students. So let's see what we have to do with vector quantities. Scalar quantities are quite known. Students are also prone to avoid vector quantities, though we actually do need vector quantities. If we have to compute the work done, work is force dot product with the path we made. Well, on many occasions this is written without vector signs, so it's just force times distance we traveled times the cosine of the angle in between the two. So if I draw here, if this is force, the vector of force, if this is the vector of the travel we did, and there's this angle in between. Without vector signs, this magnitude of the force is magnitude of force. We symbol it with the absolute sign, and scalar value of path we did is actually the actual travel we did, absolute value of this. So this is what we have to calculate. Now, for simple problems like those encountered in the first year of physics, usually these things simplifies to this, and the cosine is 1. So very simple multiplication for students. When we go to more complex problems, we know that actually this dot product or scalar product is also a correct expression in English. But don't tell this to an American. Americans don't know mathematics. So say dot, you have to say dot product for an American. And also quantities. Here on the board I am using the vector sign for vector quantities. Many textbooks use bold characters for the vectors and normal characters for the scalars. Energy, work or energy is also a scalar. So be careful about the symbols used. I will always stress the differences between our notation, American notation, and how to deal with them. So we would like to calculate this. But in order to calculate this in a simple way, this is actually a complicated way. Maybe the magnitudes of the force, magnitude of the distance we traveled, they are simple. But finding the angle in between the two, that's the difficult part of the problem. And there are even more difficult things to calculate, like problems involving rotation. In rotation, we have the vector of the angular velocity, omega. What is this vector? This is a vector along the rotation axis, if this is the rotation axis. So this is our vector, angular velocity, omega. And if we have at the position r, we have r is also a vector position, so 3 coordinates, it's a vector. We want to calculate the velocity of this point. Now, what's the simple explanation how do we calculate that velocity? Okay, we can only calculate the magnitude of the velocity. The magnitude of the velocity is now magnitude of angular velocity times, so multiplied by magnitude of position times the sine of the angle in between, if this is the angle alpha. Further, this vector of velocity should be perpendicular to the vector, to the axis of rotation. And this vector of velocity should also be perpendicular to the rotation. This velocity could not have a radial component. There is no radial component. That's the reason why it has to be perpendicular to vector r. Yet there is still something missing here. We don't have, these 3 data are not enough to calculate the vector of velocity. Why not? Because this vector here, this minus v, could also give the same result. So this vector, if I draw a vector in the opposite direction, it also corresponds to this equation, corresponds to this equation. All 3 equations are okay. We should think about where this, in which direction is this rotation. And in order to do this in a single operation, in order to define all these symbols, we say that the velocity vector is the angular velocity vector times the position of our particle. This is also, if this was a dot product, dot or scalar product, Americans this call cross product or vector. Don't say vector to the Americans because they don't know what it is. They only know the cross. Never use this word. And in this product here, if we calculate this product correctly, also the sign of the velocity is hidden in here. So we would like to have a method that we can calculate the dot product and the cross product in a simple way. without having first to find out the angles, then figuring out the direction of a vector quantity. This is quite difficult to be done. And finally, to find the sign. How do we solve this problem? We solve this thing by defining a coordinate system. And the simplest coordinate system is the Cartesian coordinate system. Usually the coordinates are denoted x, y, and z. X, y, and z, where all x, y, and z have dimensions of length, so meter usually. And they can go from minus infinity to plus infinity. If I draw the axis, I'm trying to make a 3D drawing now on a 2D board. Axis x, axis y, axis z. Always when we don't know how to solve a problem, we have in some strange coordinate system the problem, we have to convert the problem to Cartesian coordinates and back from Cartesian coordinates back to the coordinates we want the final result. Distances, of course, can only be computed in Cartesian coordinates. So distances, if I have 2 points here, point 1 and point 2. The distance between 2 points is defined by the Pythagorean theorem. So this one has coordinates x1, y1, z1, and this one is at coordinates x2, z2, y2, y2, z2. So we can calculate the distance using the Pythagorean theorem. So difference in the x coordinates squared plus difference in the y coordinates squared plus difference in the z coordinates. We can only have distances because all the coordinates have metric units here. Something that is very useful, okay, we may say that point P1 is located at the position R1, and this position is a vector. Maybe I change the color here to be better readable. And point P2 is positioned at the position vector R2. Now, how to write vectors? Well, in math, usually you wrote vectors simply R1 because you only had the coordinate system. This is x1, y1, z1. This is quite uncomfortable for us because we may have in the same problem different coordinate systems. We have to find a better way to define this system. In the Cartesian coordinate, we can define the unit vectors or base vectors of this coordinate system. Cartesian coordinate system, what we actually need is 3-dimensional coordinate systems. We have 3 unit vectors in the direction of the axis of the coordinate system. So this is unit vector or base vector 1x, 1y, 1z. This is the way we write unit vectors usually in our country. Americans use different notation. They define the unit vector as x with a hat. And this unit vector, they define it as y with a hat. And this vector, they define it as z with a hat. So letters with hats on top are actually unit vectors. What can we say about unit vectors and about our coordinate system? We said we need a three-dimensional coordinate system because space has 3 dimensions. In order to simplify calculations, we need that these axes are at right angle. So we have right angles in all these positions. So we need a coordinate system that's orthogonal. That's also a requirement we have. What does that mean? It means that 2 unit vectors, if I multiply a unit vector by itself, take a dot product. If this is a unit vector, I get here 1. If these unit vectors are perpendicular to each other, then if I multiply 2 different unit vectors, take a scalar product. Here the cosine is 0. Here the cosine was 1. Cosine is 0 times y. This is equal to 0. So this is actually unit vector, and this means that it's orthogonal, this system. In this way, how can I express this R1? I should rewrite it in this way. So unit vector in the first coordinate, 1x, times value of this coordinate, x1, plus unit vector in the direction 2, in the direction y, times y1, plus unit vector in the direction 3, times z1. So this is the notation we usually use. This is what mathematicians use. Fortunately, the mathematicians, they only have 1 coordinate system. We have many coordinate systems. In the same way, we can express other things here. So how to calculate the dot product. The dot product becomes very simple once the coordinate system is orthogonal. Because if it's orthogonal, it's very simple to calculate these components. So how do I calculate x1? x1 is simply our vector r1, dot product with the unit vector 1x, the base vector 1x. Because if I multiply this equation with this one here, you see that only this comes out as x1, while this is 0 and this multiplication is 0. Very simple to calculate. And we can also see how do we calculate here the dot product. So f dot s, this is simply now f x, the x component of the force, multiplied by the x component of the travel, plus y component of the force times y component of the travel, plus z component of the force times z component of the travel. Very simple to calculate, nothing to think. You can program a computer to do this. Here you have to watch and make several assumptions how this is rotated. Here you just program the computer does everything. The computer doesn't think, he just obeys what he told him. The more difficult thing is how do we make the cross product. So V times R. Again, we can use the orthogonal property, 3D of course, orthogonal property, but we still need some additional information for the sign of the final result. Because we may have both signs, how do we define the direction of rotation? And we define the rotation so that we have here a right-hand coordinate system. Right-hand. We want a right-handed coordinate system, and in order to keep this property, we should also write the coordinates in the same order, x, y, z, not x, z, y. X, z, y will provide the wrong sign. And how do we calculate the cross product? So omega times r, how do we calculate it? We calculate it through a determinant where we have our unit vectors in the top row, 1x, 1y, 1z. We have the components of the first vector in the central row, so omega x, omega y, omega z. And we have the components of the second vector in the bottom row, so rx, ry, rz. What this calculates out? Well, right-handed, how do we write it with the unit vectors? Right-handed, it means that for a right-handed system, system. 1x times 1y is 1z. So with these cross products, we actually define the handiness of the system, a right-handed or left-handed system. What comes out of this determinant? Of course, we may rewrite this product in the components. So component 1x, what does it contain? 1x is this subdeterminant here, so 1x is omega y times omega y times rz minus this product here, so minus omega z times ry, plus the other components, 1y, and here we put it right, plus 1z. But this is much more simple to remember when you have all these things. Now, the real problem with antennas is that the Cartesian coordinate system is not very suitable for antenna problems. Radiation usually comes out of a spot, a single spot, and goes into every direction in space. So for us, with the antennas, it's much better to use the spherical coordinate system. To use spherical coordinates, and we use spherical coordinates. Distance from the center is r, without the vector sign because it's a scalar. Polar distance theta, and longitude phi. So to introduce a new coordinate system, I will first draw a Cartesian coordinate system, and I will define the new system linked to the Cartesian coordinates. So x, y, and z. And if I have a certain point here, point that's defined by r, theta, and phi, where r is the distance from the center. Theta is the polar angle. This is actually the complement to the latitude of this point. We could also use latitude, but most books in mathematics and in physics are written using the polar angle. So this is different from geography. Use the polar angle. So latitude would be here. And I'm just trying to take a different color to have. If we make a projection of this point on the plane xy, this angle here is actually the longitude phi. And this is the projection in the xy plane, so this is actually z, the coordinate z. In Cartesian coordinates, this is the coordinate y, and this is the coordinate x. So x is here, y is this distance here, this projection in the plane xy. So longitude, polar distance, and r. Those are the values we have here. We measure both angles in radians to have simple derivations. We could measure them in degrees, but then we have problems with derivations, calculating the derivations, and we will need derivatives in our calculations. So r has dimensions of distance meters. It's always larger or equal to 0, and is less than infinity. The polar angle theta is measured in radians to have simple derivations, simple calculation. Goes from the North Pole, 0, down to the South Pole, so pi. And longitude, we also measure longitude in radians, not in degrees like in geography, but in radians. Longitude may go from 0. Here I need no units because radians actually, we don't write pi radians. We just write pi here. Radians do not have a unit. They are the natural unit for angles. That's the reason why we don't write pi radians here. This one goes to 2 pi. Always less than 2 pi because if we are 0, we are here. And this is the coordinate system that's appropriate for our spherical, for our problems in antennas. Spherical coordinates are most appropriate. How do we make calculations in spherical coordinates? That's already difficult, already thinking about geography. If I draw a globe here of the Earth, on the Earth I can draw meridians. This is the North Pole here. And I can draw parallels. How do I calculate on a globe? How do I calculate the distance I traveled? Let's take a simple example, not this example where I'm going to have changes in all coordinates. Just a change in one coordinate. Well, for r is no problem. So if I go in the direction r, so my travel, actual delta L, is actually equal to delta R. If I climb up, if I send a rocket straight above my head. So for the height, there is no problem. Our height above sea level is simply r minus the radius of the Earth. The height above sea level. In the direction theta, where do I move in the direction theta? In the direction theta, I move along a meridian. So I move here, I make this travel here. This is delta L in the direction theta. That corresponds to a delta theta. How do I get the travel in the direction theta? The actual travel I have. This delta L cannot be made equal to delta theta. This is not correct. This is not correct because the units are not correct here. All our physical quantities have units. Here I have radians and here I have meters. So this equation cannot work. How do I correct this? I correct this by multiplying this by r without the dot, because dot is reserved for dot product. Prefer not to use. If I multiply by r, then r has meters here, theta has radians that are known units. This is also meter. This is correct. This is correct because if I inflate my Earth here, I inflate a ball, then for the same delta theta, for the same polar distance delta theta, I get a longer distance. this distance is exactly proportional to the delta theta and to the radius at which radius I am traveling around. This can also be rewritten in a more mathematical form, that I have an h, a Lamé coefficient, for the coordinate theta times delta theta. This Lamé coefficient, or scale factor, makes the conversion from angular units to distance units. Even more difficult is to travel along a parallel. So what distance do I make if I go east here for a delta phi, for a delta longitude? So in the direction phi, what do I get here? So the distance I travel is actually here proportional to the longitude difference I made. But there is still something missing. The units are wrong here. They did not match from one side to the other side. And it's not enough to multiply this by r. If multiplied by r, this equation could be correct only at the equator. The equator is the largest circle, the great circle. All meridians are great circles. The equator is also, if I were here on the equator, this would be easier. If I'm located on the North Pole, things are different. Here I have to walk and swim for 400,000 kilometers to get around the world, for all possible latitudes. At the North Pole, it's enough to grab the flag that's positioned on the North Pole and walk around that flag. And I also made a trip around the world with all latitudes. So here I missed something. Not all parallels are of the same length. The smallest is distance on top, and here I have a term that's actually sine of the polar distance, sine theta. Or written in a more mathematical form, this is the scale factor, or the Lamé coefficients, for the longitude times the difference of the longitude. I can also say that the scale factor for polar distance is just r, and the scale factor, the Lamé coefficient for the longitude, is r times sinus theta. And of course, I may also define a Lamé coefficient or scale factor for r. This is simply equal to unity. There's no problem. So I do have these problems. How do I calculate these coefficients in arbitrary curvilinear coordinates? The geographical coordinates are curvilinear coordinates because meridians are not straight lines, because parallels are not straight lines. We could have an arbitrary coordinate system. I have to find the eraser. This doesn't work at all. So in an arbitrary coordinate system where I have three curvilinear coordinates, say q1, q2, q3, that have arbitrary units. I have also these Lamé coefficients of scale factors. So hi for the ith coordinate is how defined? Is defined as the partial derivative of Cartesian coordinate x over q1 squared plus partial derivative of y over q1 squared plus partial derivative of z over qi, if I said hy, qi I here and here I squared. And this could be for I is 1, 2, and 3 for the 3 coordinates. I get the 3 Lamé coefficients, the 3 scale factors for all possible coordinates. Here we already calculated these Lamé coefficients from Lamé coefficients from the simple geographical problem. We could also calculate this, and this. We could calculate using the relationship within between the Cartesian coordinates and the spherical coordinates. What is this relationship? We can simply rewrite it here. So x, y, we need x, y, and z defined by the spherical coordinates. Z is r times cosine, polar distance. X and y have the term r times sine, polar distance. And here is cosine of longitude and sine of longitude. And we can put this in the equation, and as a result, we get out this. What are the unit vectors in the spherical coordinate system? We still have to do this. The unit vectors. The unit vector 1r, or r hat in American literature, points out of the origin towards infinity, so in the direction of the distance r. 1 theta points in the direction of the unit vector 1 theta points in the direction of increasing theta, so this is theta hat with the American notation. And 1 phi is here, 1 phi points, or phi with hat, points in the direction of the increasing longitude. Of course, because we want a right-handed coordinate system, we have 3 coordinates that are always perpendicular. So we have 3D, we have perpendicular. Right-handedness is how defined? Right-handedness is 1r times 1 theta is 1 phi. Very simple. Also, if we don't know the third vector, we can simply calculate this equation here, and we can calculate this using our expression, our determinant for the cross product. A final thing that we need with the spherical coordinates is that we are not always happy with the north pole of our sphere. We would like to have the north pole located somewhere else. This is a very frequent problem with antenna arrays. How do we solve this thing? So I have to redraw the coordinate system. First, the Cartesian coordinate system, so to know what I'm talking about. So, x, y, and z. But now, for some reason, my structure of the antenna is located along the x-axis. And then I would prefer to have a spherical coordinate system with coordinates r, polar angle from the x-axis, and longitude from the x-axis. These are denoted by the suffix x here. How does now a position of a certain point, if I have a point here, on the position r, this distance is also, so I have a point that has coordinates r, theta x, phi x. Where are the remaining coordinates? So, the angle theta x is actually measured here from our new polar axis x. And the The other coordinate, I have to make a projection in the plane yz, here, to draw it exactly in the same way. This is the projection in the plane yz, and the coordinates now here are, this is coordinate y, this is coordinate z in the plane yz, and this angle I make here, this angle in the plane yz is actually phi x. For a coordinate system that has its polar, its north pole in the direction of the x-axis. Well, we could also calculate things we could also calculate things for the y-axis. We could also calculate things for an arbitrary north pole of this spherical coordinate system. But usually arbitrary, with antennas, we don't need arbitrary rotations. For antennas, it's sufficient that we have rotations at right angles, because we usually build arrays in one direction and perpendicular and another perpendicular, so in 3D in XYZ coordinates. That's the reason. So here, if we look here now at the connection to the Cartesian coordinates, so x, y, and z. So x is here r times cosine of theta x. These two have r times sine of theta x, sine of theta x. And here I have cosine of the new longitude phi x and sine of the new longitude phi x, phi x, this way. So these rotations happen quite frequently, and we will have to calculate this. It's even more difficult to make the rotation of the unit vectors. Also, the unit vectors here, they do rotate. Only the vector 1r is always in the same direction. The vector 1r here points always in the direction of, so 1r is always the same coordinate. But 1 theta x points here, 1 theta x points here, and 1 phi points here, 1 phi points here, 1 phi x points here. So theta x and phi x are now in different directions, and that's pretty tricky to make the conversion from these unit vectors to the unit vectors of the conventional spherical coordinates with the north pole in the z direction. We'll have to do, there will be occasions when we'll have to do that, this on the lectures here. So this is something. The most frequent thing we have to do, we have to make this conversion. This one is the most wanted. And by comparing these two formulas, with this formula, we immediately see where's the link. The link is, so now this cosine of theta x is sine theta cosine phi. And we will use this frequently, because most of our equations do this result. Or we may also have sine x, sine of theta x, but there is only Pythagoras that can help us. This is 1 minus cosine squared of theta x, or in other words, sine of theta x is always 1 minus sine squared of theta cosine squared of phi. An important thing to remember here, the sign of the polar distance only goes, unfortunately, here, the polar distance only goes to pi. This means that sine of theta is always greater than 1 or equal to 0. Always greater than 0 or equal to 0. This thing is always positive. Not as the square root implies positive or negative. We always have to take the positive value, because the only allowed value here is between 0 and pi. And the sign of such a theta is always positive. So that's for this hour. I tried to repeat here the math we need in our lectures. Next hour, we have to see the electric problems we meet with antennas. So we change a little bit the subject using what we said here. Not really the immediate results are still general in the vector form, but then in the our final hour today, we shall use both the spherical coordinates and the Cartesian coordinates to calculate a simple problem, the basic problem of what we are talking about in this course.